Okay, so this next section is on logarithmic and exponential equations. You've already seen these to some extent, but okay, just pass it up. What's that? Okay, just bring it up at the end. Okay, so you've already seen some logarithmic and some exponential equations, but a few of these are going to get kind of interesting. On the starter question, it says solve each one of these. So if we were going to solve this, the way we know how to solve exponential equations right now is to write both sides using the same base, right? So this is going to be 2 to the x squared, and then over here I'm going to write this as 2 to the third. If the bases are the same, then the exponents have to be the same. That means x squared is going to equal 3. And then I take the square root and I get x equals plus or minus radical 3. Everybody good with that? Okay, now do I keep both the answers? Do they both work?
No.
Do I have to throw out the negative one or anything like that?
No.
No, because think about the function or the equation that I'm dealing with. It's an exponential. We don't have any domain issues with exponentials. So I do get to keep both of those, okay? Now when I solve this one's a more difficult problem. You can't write both sides using the same base. So what do we do with that? Yeah, if you can't figure it out in exponential form, we'll write it in logarithmic form. So I can write this as log base 2 of 17 equals x. And that right there is the answer. That's the exact answer. In order to get a decimal approximation for that, you'd have to type it into the calculator. Using the change of base formulas that we learned last time. Okay, and then let's take a look at this problem right here. Haven't done these for a while. Maybe. Suggestion that we shouldn't do them at all. Okay, what do I do here? Okay, this happens to be a proportion, so you can do what we call cross products. I can multiply these two together and those two together. In the long run, that works only when you've got a proportion, a single fraction over here and a single fraction over here. What works better in the long run is to remember, you know what I need to do here is I need to cancel off everything in the denominator. So I need to multiply by an x plus 6 and an x plus 3 on both sides. If I do that, the x plus 6 cancels, so I end up with an x plus 3 times an x minus 1 on this side. When I multiply over here, the x plus 3 cancels, so I end up with the x plus 6 and an x minus 2. And then I go through and start solving. So I'd have to distribute through. This is going to give us an x squared plus a 2x minus a 3. Correct me if I'm wrong there. On this side, this is going to give us an x squared plus 4x minus a 12. Everybody okay with that? So this looks really awful. I mean, it's been awful here, it's awful there, but right now, what do we get to do? Yeah, I've got an x squared on both sides, so now I'm just solving a linear equation. So this isn't going to be too bad to finish off. I'm going to move the 2x to this side by subtracting 2x, so that's going to be gone. And then I'm going to move the 12 to the other side by adding 12, so that'll be gone. So I end up with, this is a 2x, right? And this over here, I get a 9. So I finish this problem by dividing everything by 2. So I get x equals 9/2. So there's the answer. Now, do I get to keep that answer? Does it actually work when I plug it in? What are the only two numbers that wouldn't work if they turned up in our answer set? Okay, we couldn't use a -6 and we couldn't use a -3. So we do want to be aware when we're solving an equation that you have to make sure that your answer actually works when we plug it in. Okay, any questions on this one? Did we make any mistakes? Does this look right? Everybody good with that? Okay, so then the last part of the starter question was fill in the blanks. Logs and exponentials of the same base are inverses of each other. Okay? So the nice thing about knowing that logs and exponentials of the same base are inverses of each other, that gives us another tool to solve exponential and logarithmic equations. So just like you use inverse operations to solve this right here, you'd subtract 5 from both sides, then you'd divide by 2 because that would be the opposite of multiplying by 2 and adding 5. And on this one right here, I want you to notice something. Nobody squawked when I did this right here and said, hey, you know what? This just turns into an x, and over here I've got a square root of 3 with a plus or minus in front of it. So if I were solving this one, I'd just write x equals plus or minus radical 17, right? A lot of times we don't even go through the bother of writing square root of both sides, right? Okay, well, the idea in this section is we want to be so familiar and so good at working with logarithmic and exponential functions that we can use them to solve logarithmic and exponential equations using inverse operations. So I'm going to show you a couple different techniques on each one of these problems right here. So these are exponential equations, and it says solve by writing both sides using the same base, which on this problem is very easy. They can both be written with a base of 2. If the bases are the same, the exponents have to be the same. There's x equals 4. I don't have to worry about any domain issues because it's an exponential function. I know the domain is all real numbers, so if I get that answer and I didn't make any mistakes, it's going to work when I plug it in. This problem, though, is different. You can't write 17 with a base of 2. Well, or maybe you could if you tried really hard. You might want to think about that. Okay? But we can do this. We can look at this and say, well, this is exponential base 2, and the exponent is x. I want to get that down where I can work with it. What function or what operation do we have that will undo exponential base 2? Log base 2. So I could take the log base 2 of this side and take the log base 2 of this side. These two functions undo each other, so I get an x, and over here I have log base 2 of 17. Now, you'll notice that that's the same answer that we got just a second ago, except for it's kind of flip-flopped. Does that make any difference? No, but what I want you to look at is there's something nice about this right here. You'll notice that the x stayed on the same side, so we weren't really translating this into some new form like we did on the previous problem. And what we were doing is we were taking advantage of the fact that log base 2 is the inverse of exponential base 2. Okay? It's kind of like what we did right here when we took the square root of both sides. And if you think about it that way, we could do the equivalent of skipping putting the square root on there. We could just say, hey, you know what? I'm going to take the log base 2 of this side. That's going to give me an x. And if I take the log base 2 of this side, I get 17. So there we go. Does that make sense? Okay. So those are exponential equations, and now I've got some logarithmic equations that we want to solve using the same type of ideas. So on this problem right here, there's a huge favor that's already been done for us on this problem. Can anybody tell us what it is? They already have the same base. So if that's log base 3 of the 4, and that's log base 3 of 5x, then 4 must equal 5x. And then I can just solve that equation. So I get x equals 4/5. Now, I'm going to put a dotted circle around this for the time being. Can I use that answer? Is it okay to plug that in? Okay, it is okay, and here's why it's okay. And I need everybody to watch, and I need you to think about this. It's not okay because it's positive. That's not the only reason it's okay. The reason it's okay is if I plug it in right here, this says, that's the only place where there's an x in this equation. This says log base 3 of 5 times 4/5. It's because when I plug that in, I'm still taking the log base 3 of a positive number. That's why it's okay. Whoops, that's a 4, isn't it? Okay. Bad arithmetic. Okay. That's why it's okay. Because once I plug it in, I'm taking the log of a positive, and that's what we want. Okay? So if I take a look at this problem right here, I want to solve this one using an inverse operation. How could I undo log base 8? Yeah, do 8 to both sides. So I could do 8 to this side and 8 to that side, right? Man, that is annoying. So what do these two do to each other? Undo each other. So we get x over here, and what on this side? We get 64. Okay? Okay, now, okay, what we just did on this problem right here is we did what's called exponentiating. Okay? So there's our word of the day, exponentiate. Okay? It's kind of like you guys always say, well, you square root it or something like that. Okay? That means take the square root of both sides. When we say exponentiate, we mean raise both sides and put that as an exponent with the same base. Now, I can do the same thing over here, so take a good look. I don't want that log base 3 on either side. So if I did 3 to this side and 3 to that side, that's a legal algebraic move because I'm doing the same thing to both sides, right? So if I do 3 to the log base 3 of 4, I get 4. If I do 3 to the log base 3 of 5x, I get 5x. Now, it takes a little bit of extra work maybe to write that, but the idea is really important that we're undoing these using inverse operations. Any questions? Sure? Okay. I can do the same thing on this one, the equivalent. I could do log base 2 of 2 to the x equals log base 2 of 16. These undo each other. I get an x over here. And what's log base 2 of 16? It's a 4. So I get the same answer that way. Okay, so that's called exponentiating. Exponentiating is going to come in handy when I've got a single logarithm on both sides with the same base, like this one is, or like this one, I've got a logarithm on this side and I want to get rid of that so I can figure out what it is altogether. So let's take a look at the next couple of examples. So this is example 3. It says use the properties of logs, exponentials, and inverse functions in order to solve these. So I want to know what x is. 10 to what power equals 108. Now, if I want to undo exponential base 10, what do? Take the common log. Okay, logs will undo exponentials. So I'm going to do the common log of this side. It will equal the common log of this side. What do these do to each other? Cancel each other out. Remember, when it's not written, it's base 10. So this is the answer. That is the exact answer. Yeah.
So if on the test it said just solve this, could we do like just skip the taking the common log, or just like skip it just because we know the reasoning?
Yeah, yeah. I would like you to spend some time thinking about how these are related to each other. Okay, because really changing from exponential form to logarithmic form. Okay. Yeah, in some sense it is. Okay, but it would be better if you're thinking about inverse operations because in the long run, those are much better to use. Okay, so let's take a look at this one right here. Could I just take, well, let's see, these are logs. How could I undo log base 4? Okay, I could exponentiate, but that's not the way exponents work. I can't just have this exponent minus this exponent. So I need to write this as a single logarithm to start with. Yeah.
Wait, if they all just have the same base, can't we just
Doesn't work that
pretend
way.
it's not there?
Nope, doesn't work that way. Didn't you hope that yesterday?
I hope that every day.
Okay, we'll stop that. Okay, so what we do is we'd write this as log base 4 of 3x. We're going to write this as log base 4 of 30 over 2. So this is going to be log base 4 of 15. Now, again, the logic behind this is, hey, if this is log base 4 of this stuff, and it equals log base 4 of that stuff, then this has got to equal that. That's the logic behind it. And you could just drop the logarithms, but it would be much better if you thought about how could you get rid of a log base 4? Yeah, what will undo a log base 4? An exponential base 4. So if I do 4 to both sides, this function undoes that function. That's why this side is a 3x. This function undoes this function, so that's why this is a 15. And the answer on this problem is a 5. Do I need to be careful with that? Do I just take that and say, hey, I've got the answer and I'm done? You want to make sure, at least take a look, when we plug this in, does it work? So if I plug that in here, this would be log base 4 of 15. Is that okay to take the log base 4 of a positive 15? It is. So we get to keep this, no problem there. Any questions? Okay, let's take a look at the next couple then. Okay. This is one reason why I think it's useful to think of this in terms of let's change this by using exponentials rather than writing both sides as the same logarithm, okay, or translating it into exponential form or something. This is going to be log base 4 of x. Logarithms allow us to change addition into multiplication, so that's going to be x minus 3 equals 1. Now, if I were going to take advantage of that logic, I'd have to write this as a log base 4 of something that still equaled 1. Or, how can I just undo log base 4? Yeah. So we're going to do 4 to this side and 4 to this side. These operations will undo each other, and I've got an x times x minus 3 equals 4, and from there on, I mean, it's not a cakewalk. We still have to go through and figure out what this is, but at least it's something that maybe looks a little bit more familiar. So we're going to solve that equation there, yeah.
So, if the answer, if it equals 1, doesn't that mean that x is automatically 0?
That might be one of the answers. That might mean that this stuff right here, well, let's see. If 4 to this power equals that stuff.
Can we just solve it right now?
Okay, so hold on. We're not, okay, I think you're getting these backwards. The 1's not here. It's not log base 4 of 1 equals x. The 1's over here. Okay, so it's not going to be 0. Okay. And if you were looking at it and trying to guess what one of the answers was, you might be able to guess what one of the answers, but on this problem, we're going to end up with 2 solutions. Okay? So much better to go step through the algebra. It'll definitely help us here, and it'll help us on more difficult problems. So this is going to be x squared minus 3x equals 4. Ideas? Set it equal to 0, right? So this is going to be x squared minus 3x minus 4 equals 0. This is a quadratic that we can factor, -4 and +1. So one of the answers is 4, and the other answer is -1. Do we keep them both?
No.
Okay. Is it okay to plug a 4 in? Let's check and see. This would be log base 4 of 4. Yeah, that's okay. This would be log base 4 of 4 minus 3. 4 minus 3 is 1. So this would be log base 4 of 1. Is that okay? Totally okay. So we're going to definitely keep this one. Let's plug in a -1. If I plug it in here, log base 4 of -1. Is that okay? It's not, so that's an extraneous solution. We're going to throw that one out. The only answer on that, and you can be guaranteed that on the test, and if one of these shows up on the final, which they usually do, it's going to have a couple answers and you're going to cross off one or both of them. Okay, so please make sure you're careful. Any questions there? Okay, let's take a look at this problem right here. This is a fair step up from what you've done before. This is an exponential equation. Usually we like to write both sides using the same base. You can't write 4 and 3 using the same base. If that doesn't work, then we end up undoing an exponential. Well, we've got a base 3 and a base 4. You can't undo both of them with the same exponential, or sorry, with the same logarithm. Any ideas? Say that again? No. Okay, need you to listen really carefully. Here's what we're going to do. This is a really useful skill and a good way to think about this. The variable is up in the exponent. We need to get that down where we can work with it. We don't have very many tools for working with variables that are up in the exponent, but we do have a tool that will let us bring that variable down, bring that exponent down. What allows us to change where the exponent shows up? A logarithm. Does it matter what logarithm? It doesn't matter what logarithm, okay? Any logarithm has that property. So here's what I'm going to do. I'm going to solve this one this way. I'm going to take the ln of both sides. So I'm going to take the ln of 1 minus, or 3 times, or 3 raised to the 1 minus 2y, and I'm going to take the ln of 4 to the y. They've got this power property that says I can bring this out in front. Now this one I'm going to write as, good grief. This one's pretty easy to write. Would you write this one down? 1 minus 2y ln 3, right? Do I need anything? Need parentheses. Okay, both of those were in the exponents, so both of those are what we're going to multiply by. So I now have the y's down where I can work with it, and this is where it gets a little bit interesting and kind of brain stretching here, because we're looking at this going, you know what, this looks really ugly. I've got a y here and an ln3, that's weird, and I've got a y here and an ln4 there. Okay, this is just a number, and that's just a number. So at this point, this is like solving this equation. 1 minus 2y times 7 equals y times 6. That's what it would be like. So if you were going to do that problem, you distribute the 7 through. So guess what we do here?
I thought we couldn't distribute.
Okay, you can't do this. The ln of 3y plus 1 isn't the ln of 3y plus the ln of 1. It doesn't work that way. We're taking a number and distributing it through.
Oh wait, now I'm actually confused now.
Okay, what's ln3? Grab your calculator. Type in ln3.
But Ellen is in a number,
1.098.
but it's alone, but it's
You're
not
right.
six.
That's right.
So that's
Okay,
what we
very good. ln3 is a number. That right there is a number. Okay, we're not distributing the ln. We're distributing the ln of 3. ln of 3 is a number.
But Ellen alone isn't.
It's kind of like the square
See the
root, I
difference? Yeah, square root's a function that doesn't distribute.
Can't distribute.
This isn't a function, it's just a number. Okay? So if I distribute that through, I'm going to get the ln of 3 minus 2y ln of 3 equals y ln of 4. Any questions?
Not yet.
So here's where I'd be on this problem. This would be 7 minus 14y equals 6y. So if we were solving this problem, what would we do? We'd move the 14y over, right? So we're going to take this and we're going to move it over there. I'm going to move it over there by adding 2y ln 3. So this is what I've got. ln of 3 equals y ln 4 plus 2 ln 3.
Can we just take the y out?
Whoops,
Hang on.
I need the y there.
Like, put it in parentheses?
Yep, we're going to do that. Hang on a second. We've got two y's over here. How do I make it look like there's only one y? Factor it out. So this is going to be y ln 4 plus 2 ln 3, and that equals the ln of 3. Okay, now I realize this looks pretty awful, but this is the equivalent. Okay, that's a number right here. This is a variable times, as ugly as that is, it's just a number. So it's the same thing as what we've got here. This would be 20y. Number on this side equals a number times a variable. Number on this side equals a number times a variable. It's the exact same structure. It looks weird, it looks uncomfortable, but that's all it is. Any questions? Thanks. Okay, so if I were here, if I were at 7 equals 20y, how would I solve for y? I'd divide. So I'm going to divide both sides by ln 4 plus 2 ln 3. So this side is going to be ln 4 plus 2 ln 3. And that would be the answer. Or at least one way you could write the answer. Okay, so here's where some people, I'm not mentioning any names, but maybe, no, I won't do that. Here's where you'll look in the back and you'll go, oh my gosh, I thought I did this right. You'll look in the back and the answer's not there. Your answer isn't there. In fact, I bet on this problem, that answer is not in the back of the book. What might be in the back of the book is this. Why? What'd they do? Yeah, they slid this up here and they said, oh, that's just going to be 3 squared. What probably is in the back of the book is ln of 3 over the ln of 36. That's what's probably in the back of the book.
Just leave it the first one.
Okay. Don't do what she said.
Why?
Okay.
Will I get it wrong on a test if I leave it the other way?
You will. Nobody else will, but you will. Okay. So this is simplified. That's about as simple as it gets. Is this correct? Absolutely. Is this correct? Absolutely. Is this the simplest way to write it? You bet it is. Okay? Okay. Any questions on that one? Take a good look. Yeah.
So would you want the simplest one on the test?
Yes. Yeah, I'd want that one right there. Good? Okay. Don't write this down. I just want you to watch. Watch. Okay. Let's say, I already told you I'm partial to ln. I like it because it's on the calculator. Okay. So this, you could type it into your calculator and get the ln of 3 divided by the ln of 36. You could take that number, plug it in here, and those two sides would equal each other. It would make the equation true. That's the whole point of solving an equation, right? I could do this, though. Let's say, I really want to undo exponential base 3. What undoes exponential base 3? Log base 3. So what if I did log base 3 of 3 to the 1 minus 2y, and on this side I did log base 3 of 4 to the y? Let's just look at this side right here. How does that help me here? Okay, this would be 1 minus 2y. Everybody agree with that? Okay, it doesn't really help me much here, other than any logarithm has that power property, right? So what could I do here? I can move the y out front. Remember, the problem is the variable's up in the exponent. Okay, so we need a tool to get that down where we can work with it. So this is y log base 3 of 4. That's a number times y, isn't it, Tylin? Are you texting people for the answer?
Huh?
Are you texting people for the answers?
Yeah.
Nice.
No, my friend does
Okay.
not know how to do
This is a number times y. This is a number times y, and that's just a plain old number. So again, we're in a situation where we're basically solving a linear equation. So I'm going to move this over to the other side. So this is going to be 1 equals y log base 3 of 4 minus, excuse me, that's going to be a plus 2y. Everybody okay with that? How do I make it look like there's one y? Okay, we're going to factor that out. Log base 3 of 4 plus 2. Now that is just the log base 3 of 4 plus 2. Okay. And then the last thing I need to do is just divide by that. So here's what we get. I get y equals 1 over log base 3 of 4 plus 2. And that entire thing would be in the denominator. So this right here would be a perfectly good answer. Now, if we did this correctly, grab a calculator. This is the ln of 3 over the ln of 36, right? ln of 3 divided by the ln of 36. Okay, take that number, plug it in, it should make it true. Let's see if we get the same thing if we do this one. Now, this was a little bit shorter. What's wrong with this expression right here as far as checking it in the calculator? You can't do a log base 3, so here's what you'd have to do. You'd have to do ln 4 over ln 3 plus 2. That's what you'd have to type in the calculator. So let's see what we get here. This would be 1 divided by, all of that's going to be in parentheses. So I'm going to start a set of parentheses here, and I'm going to say I need ln 4 divided by the ln of 3, and then I need to add 2 to that, right? Exactly the same answer. Okay? Okay, why would using the ln be a little bit better? Because it's on your calculator, okay? And this is just a nice kind of closed form here. This looks a little bit ugly, okay? You could do a log base 10 also. Any questions? Yeah.
Is there an easy way to convert the first answer to the second answer?
To make these two look the same?
Yeah.
Sure. Once you get right here, get a common denominator on this one. So common denominator here. Put those together and then use the properties of complex fractions to simplify it. You can get these two to look exactly the same. You can turn one into the other. Much easier to go from here to here than try and make the first one we got look like the second one that we got. Okay, that'd be kind of a mess. Okay, any questions? Okay, go ahead and flip the page over then. Let's look at these problems. These are really good applications. I'm hoping that this looks somewhat familiar. What if I did this? How many terms? We've got 3 terms. If I've got 3 terms, then I've got a trinomial, right? Is this true? Is that true? So what do I have here? What technique could I use to solve this? Who said that? Substitution. I could say u equals 2 to the x. So this is u squared plus u minus 12 equals 0. Solve that quadratic. Multiply to be negative 12, combine to be positive 1, positive 4, and negative 3. So that means u equals negative 4 and u equals positive 3. I'd be done if this problem were about u's. It's not about u's. What's it about? It's about x's. So now I need to reverse that substitution. I need to replace this. So instead of writing u equals negative 4, I'm going to write 2 to the x equals negative 4. And instead of writing u equals negative 3, I'm going to write 2 to the x equals, positive 3. Okay? Now take a good look at this one right here. 2 to some power equals negative 4. No solution. You can stop right there. No answer comes from that. 2 to some power equals 3. Sure. Now, you could do it this way. And again, this is why I like you to think about how logarithms work and about how inverses work and stuff like that. If I were to do this problem and take the log base 2 of both sides, I get x equals log base 2 of 3, right? If I use the change of base formula so that I can write it down not just exactly, but that would be the ln of 3 over the ln of 2. And then I can get a decimal approximation for that. Okay? So we could just type that into the calculator. If somebody could do that really quickly, I'd appreciate it. But then we get not only the exact answer and a couple different forms of the exact answer, we get a decimal approximation. What is it? 1.585. Okay? Any questions there? So this is a really good problem because think about how many things it puts together. It puts together exponentials, logarithms, puts together quadratics, factoring, all sorts of stuff. Even domain issues come out on that problem right there. Okay, any questions? Okay, let's take a look at the next one. This also is an exponential equation. Let's see if we can solve this one. The variable is right up there, right above the 5. Ideas on how to solve this one. The first thing we'd want to do is we kind of want to isolate that exponential expression. Okay, whenever we're trying to solve an equation, it's usually a good idea to start isolating wherever that variable term is and then the function with that variable. So this is going to be, let's see, 4 goes into both of those. So this is going to be 7/2 equals 5 to the x. I need to undo exponential base 5. Log base 5 of 7/2 equals x, right? Isn't that what it is? Good there? Okay, this would work. That works fine.
Or you have to get the number. Do you have to get the number? Is it better to get the number or leave it exact?
This is exact. It's better to leave it exact because most people can, well, most of the time you can figure out how to plug it into your calculator. And we'll look at this a little more in depth. Watch, please. Could I do this? Could I do the ln of 7/2 equals the ln of 5 to the x? Yeah, I can. I can do that. I can bring the x out front. So I'll write another line. ln of 7/2 equals x ln 5. And then how do I get the x by itself? Divide by ln 5. So I'll divide both sides by ln 5. So I get x equals ln 7 halves over, ln 5. Okay, here's the problem. You probably won't find either one of those answers in the back of the book. You might, but I doubt it.
See, this is why I don't like that.
What you're probably going to find is, okay, watch, think about this. If you had to type this into the calculator, you'd have to use the change of base formula, which means you'd have to find the ln of this and put it over the ln of 5. You'd have to convert it to this form anyway. Can you see how those are related? If you wrote this in exact form, it might look something like this. Ln of 7 minus ln of 2 over ln of 5. Do you see what they did there? Got rid of the fraction, right?
Yeah.
Ln 7 minus ln 2 divided by ln 5. This is probably the way it looks in the back of the book. If you were going to type that into the calculator, all you'd have to do is start a set of parentheses, type in the top, then divide by the bottom. Okay? All three of those are different forms of the exact answer. That's probably what you're going to see in the back of the book. So just because your answer doesn't match up with the back doesn't mean you did it wrong. Okay? Yeah.
So on the test, if we put like either of those answers, are we good?
We'll talk, when we get closer, we'll talk about how to write it. Okay? If it were a test, I'd much prefer this one over the other two. Okay? Okay, let's take a look at this problem here. Now think, I've got an ln on both sides. I could exponentiate with a base of e, or I could look at this and say, well, wait a minute, I can't just blindly exponentiate here. What do I need to do with that too? Right, I need to use that power property so that I have a single logarithm on this side equaling a single logarithm on this side. That way, when I exponentiate, they both get undone, and I get x squared equals 16. I finish this off by taking the square root, and I get plus or minus 4. It's literally that simple, except for one tiny thing. What have I said from day one in this class, especially if you were in my 10-10 class? What do you always have to be careful of? Domain issues. This is an ln. It's a logarithmic equation. You can't plug in something that makes it so you're taking the ln of a negative or a 0. So can I plug in the negative 4? No. Answer there is no. Okay, so I cross that off. The only answer is x equals 4. Yeah?
Why not? Because if you square, it's just going to be positive.
Okay, look where it is to begin with. Okay, it was just an ln of, it would be an ln of negative 4 with a 2 out front. Okay, so it wasn't the ln of negative 4 squared. It was 2 times the ln of negative 4. Taking the ln of negative 4 isn't okay. If they had written this up here in the problem to begin with, then it would be okay. Okay? It's how it was written originally that we have to worry about. Okay, let's take a look at this. Ideas? What is it, Amelia? What are we going to do?
Make them the times.
Okay, so this is going to be x minus 1, x plus 1 equals the log of 8, and then exponentiate with a base of 10, right? So I get x minus 1 times x plus 1 equals 8, and then I solve that. I'm going to get two solutions. I'd want to make sure that I make sure both of them work. Let's see, so this is going to be x squared minus 1 equals 8. Move that over. And then I think you can finish it from there. Okay? So you finish that. Okay, I want to take a look at the last couple. Let's take a look at the one right below it. You can't undo an exponential base e and an exponential base 5 with the same function, so what choice should we make? Probably ln, because it's going to undo one of them and it's also on our calculator. So if I take the ln of both sides, here's what I get. I get 1 minus x in parentheses times the ln of e equals x. Yeah, it does. Hang on a sec. Wait a minute. Taking this, don't these just cancel off? Doesn't this turn into 1 minus x?
I thought so.
Okay, what's ln of e? Yeah, ln of e is just 1. Okay, so it works either way. So this side is just 1 minus x. This side is x ln 5. So if I've got 1 minus x and x ln 5, I'm going to move the x to this side. Factor. And then divide. So my answer on this problem is going to be 1 over ln of 5 plus 1.
That will be
Will the back of the book say that?
Yeah, most likely. Any questions? Sure? Okay. We won't worry about that one right there, although that's a pretty interesting problem. You might want to think about how you do that. On this one right here, you can't undo them both. What logarithm? ln or common log. I don't care which. I like ln. It's 2 letters rather than 3. Okay, that's pretty much what it comes down to. So this is going to be the ln of 5 to the x minus 2, ln of 3 to the 3x plus 2, x minus 2 ln 5, 3x plus 2, ln 3. Any questions to there? What next? Distribute through. So we're going to distribute through here and here. So that gives me x ln 5 minus 2 ln 5 equals 3x ln 3 plus 2 ln 3. Next.
Move the x, the 3x. I like.
Yeah, x is on the same side. I'm going to move this one over here, and I'm going to move that one over there. That's going to turn this one positive. It'll turn that one negative, but that's not that big a deal. So this is going to be x ln 5 minus 3x ln 3 equals 2 ln 3 plus 2 ln 5. How do I make it look like there's only one variable over here? Factor it out. See how these are the same steps every time? So this is going to be x ln 5 minus 3 ln 3. Now some of you may be looking at this and say, hey, wait a minute, we can do something with those. Okay? And this one is 2 ln 3 plus 2 ln 5. So just to save a little bit of work and some space in writing, how am I going to get the x by itself? Yeah, I'm going to divide, right? So this is going to be divided by ln 5 minus 3 ln 3. And this right here is a form of the correct answer. Could we clean it up just a little bit?
Probably.
I'm not going to write 2 ln 3. I'm going to write 2 ln 3. I'm going to write ln 9. I'm not going to write 2 ln 5. I'm going to write plus ln,
10.
close, 25. And on the bottom, I'm going to write ln 5 minus the ln of 27. Now, I probably would not change this into division. I'd either leave this answer like this, or maybe write ln 225 divided by the ln of 5 minus the ln of 27. That probably would be the shortest way to write it. Okay?
Why would you put it?
Have complex division.
Because then you'd be taking the ln of a fraction. Okay?
Complex
It's just personal preference. Okay, that's probably the best way. Any questions? What's that? 9 times 25 is 225. Okay? One last thing, let me just have you watch. Okay, one of the bad things about this is this has a fraction in it, right? It's got a denominator. That's a little better, right? The next worst thing is this has a negative exponent. Okay, so stop and think about what that means. What it means is this is e to the x plus 2 over e to the x equals 3. So if that's in the denominator, let's multiply by e to the x. That's going to give us e to the x squared here. What's it going to give us here? 2. And what's it going to give us here? 3e to the x. Now, how many terms does that have? What is that? Substitution. Okay? So a little bit of algebra, getting rid of that e to the negative x by basically multiplying everything here by e to the x. E to the x squared cancels off, 3e to the x. Get an equation that we can finish off using the substitution technique. Okay? All right, that's it. Let's see, today's Wednesday?
Yep.
What do we got on the calendar tomorrow?